So let me then talk about what we will discuss in this lecture in those couple of minutes. Today I'm planning to look at the properties and geometry of geometric. There is more to quantum geometric related with the subject of curvature and such, but I'm planning to leave curvature for tomorrow's lecture because I want to do it in a detailed fashion. And tomorrow, hopefully, we will be discussing geometrics, Kobayashi and correlatorate metrics. At least we will begin to give definitions and sense of what they look like.
I think we start now, if you want.
Okay then. So hello everyone. Yesterday we made a short review of complex analysis and gave some preliminary definitions from differential geometry. Today I want to discuss pangeometric in a detailed way, well, detailish way. So today we will turn our attention to the pangeometric. First, recall that the pangeometric on the unit disk is given by rho z 1 over 1 minus square of absolute value of z. Now from now on, we will call a holomorphic one-to-one onto map as a conformal map. Now again, there is more to this conformal map business. I strongly recommend you to review the subject from a complex analysis book. Alfors does it in a detailed way. Also, Dominant's book does it in an enjoyable way. So you can check any complex analysis book for detailed information, detailed knowledge about conformal maps. First, I want to look at these isometries under this pangeometric. We have a proposition. We take the pangeometric on the unit disk D. Then every conformal self-map of the unit disk is an isometry of the pair unit disk with pangeometric with itself. So this means that conformal self-maps of the unit disk preserve distance under pangeometric. This is something important. So let's look at how we can prove this. What we need to show is if H is a conformal self-map of the unit disk, then the pullback metric of Poincare with respect to H is equal to pangeometric. Now, if we write the definition, pullback metric of Poincare with respect to H is equal to the value of the metric at Hz times the absolute value of the derivative of H at the point Z. So we take a conformal self-map of the unit disk. Then we know that H is a composition of a rotation and a Mobius transformation. So we examine the two cases. H is of the form of either a rotation, then Hz is equal to mu z with some mu with absolute value 1, or H is a Mobius transformation. So let's look at the case 1. If H is a rotation, if H is equal to mu z, then we have the derivative of H, the magnitude of the derivative of H is 1. So when we put everything in the equation, we get the pullback of rho with respect to H is equal to 1 over 1 minus absolute value of mu square times absolute value of z square, but absolute value of mu is equal to 1, so this thing is equal to rho z. So this proves the case when H is a rotation. If H is a Möbius transformation, then we calculate Hz is equal to, Hz is of the form Z minus A over 1 minus conjugate AZ, where A is a point in D, and we calculate H prime, the absolute value of H prime Z, that is equal to 1 minus absolute value of A square over absolute value of 1 minus conjugate AZ square. So we put that in the equation and do the necessary calculations and find out that it is actually equal to rho z. So when you take in a conformal self-map, it is a composition of these two. So actually we have our results. After doing this, we want to explicitly calculate the point coexistence between 2 points. We have a formula for that. If you take any 2 points in the disk, then the point coexistence of P to Q is given by 1/2 logarithm of this nice looking fraction. Now, this looks a bit tedious, but it's actually, the idea is not that problematic. The idea is simple. First, if you remember, we already solved this for the case P is equal to 0 and Q is equal to R plus I0. We used 1 minus epsilon instead of R. If you remember, we showed gamma t is equal to t when t goes between 0 and 1 minus epsilon is of the least length from the point 0 to 1 minus epsilon. This was left as an exercise, and it is still an exercise if you haven't looked at it yet. And in an example, we calculate the length of gamma, and it was L rho gamma was 1/2 ln 2 minus epsilon over epsilon. Now, instead of 1 minus epsilon, we are here taking R. So if we turn everything to R, the distance from 0 to R is 1/2 ln 1 plus R over 1 minus R. So the given formula is true when one of the starting point is origin and ending point is on the real axis, positive real axis. So we want to look at the general case. For that, we consider the Möbius transformation. We sent 0 to P by Möbius transformation Z minus P over 1 minus conjugate PZ. Now, note that we have phi P is equal to 0 and phi Q is equal to Q minus P over 1 minus conjugate PQ. Now, Möbius transformations are conformal, so phi preserves distances under prime parametric. So we have dpq to be equal to the image of P under this Möbius transformation to the image of Q under this Möbius transformation. And that is equal to d rho to phi Q. Now we can always find a rotation, Rz, that takes phi Q to the point absolute value of phi Q. This absolute value of phi Q is on the real axis. Rotations are conformal. So we have this equality. D0 phi Q is equal to d R0 R phi Q, and that is equal to D0 absolute value of phi Q. Finally, since we already know the distance formula from point 0 to a point R on the real axis, we can put R is equal to absolute value of phi Q, and that is equal to P minus the absolute value of P minus Q over 1 minus conjugate PQ in the formula to get the desired result. So after doing this, we can state, can talk about the topology of the panparametric, topology of the disk induced by panparametric. We say that it is equal to the usual Euclidean topology. Now this is an important result. To prove it, first recall that from your points at topology classes that two topologies are the same if and only if the basis for one of these topologies can also be used as a basis for the other topology. So let's rho 1 be the panparametric, rho 2 be the Euclidean metric. We take a neighborhood basis at the origin for panparametric. Rho 1, 0 r, z such that the Poincare distance from 0 to z less than r. We take the open moles. By the distance formula, we have distance from 0 to any z is equal to 1 over 2 logarithm 1 plus absolute value of z over 1 minus absolute value of z. This should be less than r. But if this is less than r, the absolute value of z is less than e to the power 2 r minus 1 over e to the power 2 r plus 1. Or if you want to express it differently, this is tangent hyperbolic 1 over 2r. So this means that if we take s is equal to tangent hyperbolic 1 over 2r, we have b rho 1 0r is equal to b rho 2 0s. So these both also form a basis at the origin for Euclidean topology. This means that the two topologies are the same at the origin. What about the other points? Now we can move the origin to any other point A in the disk by using the Mobius transformation. We send z to z plus a over 1 plus absolute value, 1 plus conjugate a z. Then, since Poincare metric is invariant under Mobius transformations, and Mobius transformations take circles into circles, and you should remember why. So the two topologies are the same at every point. Now, we also have to look at this thing. Yesterday, we said that if the metric is, if this space equipped with our metric is not complete, then we may have some problems for finding the least possible length curve. So we have to clarify that for Poincare metric, and we have unit disk equipped with Poincare metric is a complete metric space. And the proof is left as an exercise. This is an exercise of classical analysis. All you need to do is take an arbitrary Cauchy sequence in D with respect to the Poincare metric, Cauchy of course, and that then show that it converges inside D, inside the point D in Poincare metric. So for that, you will need the formula, distance formula, but apart from that, it's a classical exercise about series. Now we established the basics. We want to analyze the geometry given by the Poincare metric. First, I want to look at the lines or curves of least length in this geometry. We take any 2 points in the disk. The curve of least Poincare length connecting P to Q is given by this nice little formula. Gamma PQT is equal to T times fraction Q minus P, 1 minus Q conjugate P plus P over 1 plus T conjugate P, q minus p over 1 minus q conjugate p, when t is between 0 and 1. Again, the formula looks tedious, but the idea is actually simple. We consider the Mobius transformation. We send 0 to p, z minus p over 1 minus conjugate pz. Now we already know the shortest path from 0 to phi q is the curve tau t, which is equal to t times phi q. Now we have phi sends p to 0. The inverse of phi sends 0 to p. And the inverse of phi composed with tau sends 0 to p. Phi takes back pq to q. And when you compose it with tau, it sends 1 to q. So we carry our starting point p to the origin by a Mobius transformation, find the shortest path in this location, and come back with the inverse of our Mobius transformation to write the formula of the curve. Mobius transformations and the inverses are Poincare distance preserving. So the curve we want, we can find it in this way. So the curve is actually inverse of phi composed with tau t, and now you write it in the equation explicitly, you get the formula given by this long function. Now, let us look at these curves more closely. Gamma PQs are the images of line segments. You take a line segment and you look at its image under a linear fractional map. So what they should be is either a line or a circle in Euclidean sense. So if 0, P, Q are collinear, you can check that the given formula reduces to a line passing from the origin. But if not, you can let t is equal to infinity. Of course, here we took t between 0 and 1, but you can send it to infinity and see what happens. If you do that, you get a third point, which is 1 over conjugate b. This point is also on this circle. Now you can find the Euclidean center and the radius by classical computations of Euclid geometry. Now if you do that, you get the geodesics of this so-called geodesics of this geometry. If you see the equatorial, the lines passing from the origin are lines, straight lines in the Euclidean sense as well. The lines, shortest paths not passing from the origin, are actually a part of Euclidean circles. And these circles are always orthogonal to boundary B because we formed them by composing a line passing from the origin and the conformal angle preserving one. So when they intersect the boundary, they are at a right angle.
Buket, would you like to start?
Yes.
I think you can also check the chat and see the question, right? Did you saw the
questions?
Emmanuel asked some question about what does the picture show again? The time.
Yeah, I saw it right now. It shows the geodesics in hyperbolic geometry, of course. That's what they call at that time. It's done by Escher. It's, I think, circle limit 1 or 2. Escher is, you know, MC Escher is an artist.
Yeah.
He did quite a lot of work about hyperbolic geometry, and there are also articles, papers about mathematics of his paintings. These are a series of woodcut paintings, circle limit series, from 1 to 4, I guess.
And also another question, the tiles have a equal area?
I'm not sure. I have worked on them quite a long time ago, and I don't know about the area. But there is, in the references I gave, Coxeter book. It's about the commemorating the life and works of MC Escher, but on the second part of the book, there are quite a lot of studies done about the mathematics of Escher's paintings, and these are explained. Every sort of detail is explained in that papers, articles. So you can find the answers, detailed answers there, I guess.
Okay.
Yes, there are a lot of papers written on that in math magazines and popular and otherwise.
Okay, thank you. I think you can share your screen.
Okay. I almost forgot.
Okay, we see now. Okay.
So now you want to characterize point parametric. We have a neat characterization. If there is any metric on D, for which every conformal map on the disk unit disk is an isometry of the pair with itself, then this metric is a constant multiple of the point parametric. So this means that every metric we form by these isometries, it is actually kind of point parametric. So the proof is easy. You know that every conformal map of the disk is an isometry. And in particular, if you fix any z0 in D, the map given by this z plus z0 over 1 plus conjugate z0 z, this Mobius transformation, is an isometry. So we have the pullback of this new metric with respect to h is equal at the point 0, the value is equal to the value of this metric at the point 0. Now we have h prime 0. If we compute it, this is equal to 1 plus absolute value of z0 squared, and h0 is equal to z0. We put them in the equation, and we get rho z0 is equal to 1 over 1 minus z0 square, absolute value of z0 square, rho z0, and that's equal to the value of z0 in point parametric times a constant, which is the value of 0, the value of this new metric at the point 0. Z0 was arbitrary, so this completes the proof. So we determined that conformal set maps are isometries with respect to point parametric. In fact, we can say more than that. We can say we have this proposition which says that if you take any continuously differentiable function and point parametric, if f is an isometry of the pair disk point parametric with itself, then then F is actually holomorphic. Since F is also one-to-one onto, F is conformal, so it is a composition of a Möbius transformation and the rotation. So we can actually show that F is conformal directly, but first we need to examine the case where the value of 0 with respect to our function is equal to 0. This is the case 1. For a positive r, we take the circle, Poincare circle, centered at 0 with radius r. Since we are using Poincare metric, CR is an Euclidean circle as well, but its radius is e to the power 2r minus 1 over e to the power 2r plus 1. F0 is equal to 0, and F is an isometry, so we have FCR is equal to itself, CR. Now, take a point in this circle, then if P is an element of this circle, so the absolute value of Fp is equal to P, absolute value of P. So we have Fp minus F0, absolute value of Fp minus F0 over absolute value of P minus 0 is equal to 1. So when we let r to infinity, we get the derivative of f at the point 0 to be 1. This means that f is conformal at the origin. For a detailed discussion of how this happens, you can see Alfors or Gamel's complex analysis book. But we will leave it at that here. Since f pulls back the metric row, we can now be sure that the derivative of rho at the point 0 is different from 0. For general case, we take an arbitrary z0 in the disk. We let w0 to be fz0. We define a Möbius transformation, as always, that takes that to minus z0 to minus. We define two Möbius transformations. And then we define a function, g, by the help of this Möbius transformation. We compose phi with f and then c. Then if you look at this new function, the value of 0, the value of g0 is equal to 0, and these are all isometries, so g is also an isometry. This means that g is conformal at the origin, but phi and c are conformal on the whole disk, so f is conformal at z0. Since f is an isometry, we have the derivative with respect to z is different from 0 at every point, so f is holomorphic. So after this, we have another proposition. We take a continuously differentiable mapping of the disk to itself. We assume that f is an isometry if the value of f at the point 0 is equal to 0, and the derivative of f at the point 0 is equal to 1, then fz is identity. Now, by the previous proposition, we know that f is holomorphic. Since f0 is equal to 0, f is 1 to 1 and onto, is f0 is equal to 0, f is 1 to 1 and onto, f must be a rotation. This means that fz is equal to mu z with absolute value of mu is equal to 1. But the derivative of f at the point 0 is equal to 1. It is given in the assumptions. So we actually have mu is equal to 1. Therefore, f is the identity map. So we have a corollary. We take two isometries and a point in the disk. If f0 is equal to fz0 is equal to gz0, and the derivative of f at the point z0 is equal to the derivative of g at the point z0, then these two functions are equal. We first note that g to the minus 1 is also an isometry. We gave this yesterday, I think. So again, we take the Mobius transformation, which takes 0 to z0. Then the inverse of this Mobius transformation composed with the inverse of g, composed with f, composed with the Mobius transformation is equal to z. And if we rewrite this in another way, this means that gz is equal to f. Now, yesterday we remembered Schwarzschild lemma. Now we want to look at it again, but with a geometric interpretation. We take a holomorphic function in the disk. Then we say that f is distance decreasing in the pan-parametric. What does this mean? This means that for any z in the disk, we have the pullback pullback distance of pan-parametric with respect to our holomorphic function will be less than or equal to the value of the point of the value of pan-parametric at the given point. So if we say it in another way, this means that if we take a gamma, a curve from 0, 1 to d, we want it to be continuously differentiable, then the length of this gamma composed with our function, holomorphic function, with respect to the pan-parametric is less than or equal to the length of gamma with respect to the pan-parametric. Or, if you want to express it in another way, if PQ is 2 points on the disk, in the disk, then we have the distance from FP to FQ, one pair distance from FP to FQ is less than or equal to the distance from P to Q. So Poincare distance metric is distance decreasing. Now the proof is, well, actually this is just rewriting Schwarzschild lemma, the second part of Schwarzschild lemma. If you remember, the Schwarzschild lemma says if f is a holomorphic function on the disk, then we have the derivative of f, absolute value of the derivative of f, is less than or equal to 1 minus absolute value of fz square over 1 minus absolute value of z square. This is the second part of Schwarzschild lemma. Now, if you, f star rho z is equal to absolute value of f prime z times rho fz, and if you write this thing neatly, this is actually equal to absolute value of f prime z over 1 over 1 minus absolute value of fz square, and this is less than or equal to 1 over 1 minus z square. And this is rho z. So this is nothing but rewriting the Schwarzschild lemma in terms of our new definitions. The others, the length of the gamma and distance formula, are just writing the definitions of length and distance formula, nothing more. So we have a theorem, Parker-Street. We take a holomorphic function. We assume that the image of this function has compact closure in D. Then there is a unique point inside our disk such that Fp is equal to P. This is a fixed point for F. So this means that if F sends a disk relatively, if the image of F is relatively compact in D, then F has a fixed point. Now, for the proof, since the image of F has compact closure in D, it sits away from the boundary. So we can always find an epsilon such that when Z is on the boundary or outside the boundary, the distance between this M and Z is greater than 2 epsilon. If you look at the image, you can always find such epsilon.
Buket, there is a question. Isn't it a corollary of Brouwer fixed point theorem?
I think so, yes.
Okay.
Yes, I believe so. Okay, so we fix Z0 in D. We define a function, gz, with fz plus epsilon times fz minus fz0. Then G is also holomorphic. Why? Because only addition of a holomorphic function and a constant. And we have the derivative of G at Z0 is equal to 1 over epsilon times f prime Z0. So G is distance decreasing in the Poincare metric. So we have G composed with rho at the point Z0 is equal to 1 plus epsilon times f composed with rho at the point Z0 equal to rho Z0. Note that this inequality holds for any Z0 in V. If we express this in distance form for PQ in the D and the Poincare distance, we have dFP to FQ is less than or equal to 1 over 1 plus epsilon times dP. Note that this also says that F is a contraction. Now, if you remember contraction points, a contraction map is defined by if the distance between Fp and Fq is less than some constant times distance times distance from P to Q, then it is a contraction map. And in complete metric spaces, contraction maps has a unique fixed point in the space. So this basically says that D equipped with Poincare metric is a since it is a complete metric space, F has a unique point in the inside D. So there is a corollary, of course. If F is as in the theorem, I mean it's the closure of its image is compact in the unit disk, and if P is a unique fixed point, then if we take iterates F composed with F composed with F composed with F, these converge uniformly on complexes to the constant function. Now, to see this, we define Fn to be F composition with itself n times. And we define our balls, closed balls, centered at P with radius R, to be the...
Buket, there is another question.
Okay.
For the existence part, yes, but the Brouwer fixed point theorem doesn't assert unicity of the fixed point.
Uniqueness of the fixed point. I couldn't hear you.
For the existence part, yes, but the Brouwer fixed point theorem doesn't assert unicity of the fixed point.
Yes, I mean, the uniqueness is also something that has to be proved. But I mean, these are just, you can arrive at this conclusion on different contexts for different subjects. Basically, this is coming from the contraction maps, the fixed point. The general setup is contraction maps has a fixed point and it is unique, incomplete metric spaces. For different setups, this is proven with different assumptions, I mean, here we do it on the unit discrete Poincare metric. And I really don't remember the exact assumptions and the proof of graphic theorem.
Okay.
So I just assumed that it was proving uniqueness as well. Anyway, so shall I continue the proof?
Yes, of course.
Okay. So what we want to do is we want to take the iterates. Let me see this again. We have a series of holomorphic functions. This series is constructed by times. We say that these series converge uniformly on complexes to the constant function P. So we define Fn to be its composition with itself n times. We take some balls centered at P and with radius R, Poincare distance radius. Now F is a contraction, so we have the image of this ball under the map F is actually is actually a subset of this ball centered at the origin with radius 1 over 1 plus epsilon. Because if you remember, we have this thing. So if you do this, if you apply this to Fn, we see that the image of this ball is a subset of the closed ball with center P and radius R over 1 plus epsilon to the power n. And if you look at these balls, if you take the union of these balls with center P and radius J, where J is a integer, positive integer, you get this itself. We are talking in point parametrics here. So radius can go and does go to infinity. So, but we already showed that these open balls are open sets in Euclidean topology because their topologies were the same. So if you take a Euclidean compact K in D, we can always find a J0 with K inside one of these balls, centered at P and radius J0. So this implies the image of Fn, the image of K with respect to Fn is a subset of this image of ball centered at P with radius Z0 under Fn, and it's a subset of ball centered at P0, centered at P with radius J0 over 1 plus epsilon to the power n. And this thing goes to the point P as n goes to infinity. So this is all for today. I have some further reading references. There's a section I omitted. It talks more about the historic aspects of hyperbolic geometry. This is quantum parametric is historically called hyperbolic geometry, if you know. It was a revolutionary mathematics at that time. Jonas Bolyai, I think, and Lobachevsky were the first to discover these non-Euclidean geometries, and everything was about the fifth postulate of Euclidean geometry, the parallel postulate. If you remember, fifth postulate says if you have a line and the point outside that line, there is exactly one line you can draw parallel to it. Now, Bolyai and Lobachevsky showed that this is just optional. I mean, in hyperbolic geometry, you can, from a point outside of a line, you can draw infinitely many lines that doesn't intersect the first line. So there is a historical aspect to this point parametric. The first and last reference are Bolyai's and Lobachevsky's own writings. They are all in public domain. I included the links here where you can find those documents. If you are artistically inclined, there's paintings of Escher circle limit series. You can also find it in wiki common source. On the internet, you can find and look at the woodcut paintings. And this second reference is there are papers, there are articles which examine the mathematics in Escher's paintings in a detailed way. And there are interesting things. The fourth reference is the textbook. It is always a good idea to have a look at the textbook, and Franz wrote it in a very enjoyable way. And that's all for today. Today was a short class, but I don't want to pass to the subject of curvature because I also want to give correlatory and some new metrics, and I don't want to divide the subject into two. So tomorrow we will start talking about curvature and define some new metrics.
Okay, there is some questions and comments in the chat. And if you want to ask a question, you can unmute yourself or you can write down the chat. I can ask for you.
I'm now I can access chat box. So yeah, the fixed point theorems, I really don't remember exactly the if Brouwer fixed point theorem does assert unicity or not, but fixed point theorems are usually stated with this logic. General outline is like this. Why can we find such a J0? Because it's, I mean, these are the basis of a topology. So you can, when you take a compact set, it has to sit inside one of these balls. You can find a ball that covers this compact set. It's point set topology. I mean, playing with neighborhoods and such. And of course, K is compact, you are right.